Welcome back to the deep dive. Today we are jumping straight into something that really challenges a core belief about a major AI architecture.
We're talking about mixture of experts, or MoE models.
Exactly. And the whole idea has always been specialization. This clean divide and conquer approach where a math problem goes to the math experts. Simple.
Well, it turns out it's not so simple. The paper we're looking at is called The Illusion of Specialization, and that title says it all.
An illusion. Okay, so what did they find instead? What's behind the curtain?
They use this framework, committee audit, to trace how data actually moves through the model, and they found what they call a domain-invariant standing committee.
A standing committee. It sounds official. What is that in AI terms?
Think of it as a small, stable group of experts, maybe just 2 to 5 of them, that act as a hidden generalist core.
A generalist core. So no matter the topic, finance, biology, whatever, the same small group is handling the work.
That's what the data shows. This tiny coalition just absorbs most of the computational load, regardless of the domain.
Okay, let's talk numbers then, because this sounds, well, it sounds inefficient if you're building a huge specialized system. How centralized is this across models like Olmo or DeepSeek?
The numbers are, frankly, extreme. They use Jacquard's similarity to measure the overlap of the top experts across different domains.
And what did that show?
The average overlap was consistently around 0.87.
Wait, 0.87. So 87% of the time, the system is using the same top experts for supposedly different tasks.
Precisely. The specialization we thought we were getting, it's just not the main story here.
That's incredible. What about the concentration of work?
Even more striking, they measured the Giannini coefficient, which, tracks inequality.
Right, how the workload is shared.
And it was consistently above 0.88, sometimes even over 0.94. This means a tiny handful of experts is taking on up to 70% of the total computational mass.
And this isn't just a fluke at one layer of the network.
Not at all. This structure, this standing committee, it's there across all layers, shallow, middle, and deep. It's like the model's permanent backbone.
So if the committee is doing most of the work, what kind of work is it? Is it handling the really complex domain-specific stuff?
It's actually the opposite. They found a very clear functional split. The standing committee handles 2 domain-agnostic things.
Okay.
First, the syntactic backbone. High-frequency words like the, E-E-N-E, the glue of the language.
The basic grammar makes sense. What's the second thing?
It handles the logical framing. So functional tokens like which, what, suppose, and even question marks. It sets up the reasoning structure.
So it builds the logical and grammatical template. And the other experts?
The peripheral ones. They only get called in for the really specific low-frequency knowledge. Think chemical symbols, financial jargon, things like that. They fill in the blanks, but the committee draws the outline.
This all feels like it's an emergent property then, something the model figured out on its own because it works best.
It certainly appears to be an emergent optimization. But here's the tension. Our standard training practices for MoE models directly fight against this. We use what are called load balancing auxiliary losses.
Right, to force the model to use all the experts equally, to enforce fairness.
Exactly. We're trying to spread the work out, but the model wants to centralize it on this highly efficient core.
No, we're literally spending computational budget to prevent the model from doing what it finds to be the most effective thing.
That's the conflict in a nutshell.
Yeah.
We're fighting against its natural optimization behavior. This research really shows that even in these sparse systems, you need a powerful generalist core to hold it all together.
Which brings up a fascinating thought then. Since this centralization is natural for MoEs, what if we just stopped fighting it? What if future architectures were designed to embrace this core periphery structure from the start, instead of trying to force a fairness that the model doesn't even want?
Okay, let's unpack this.
Let's do it.
We're diving into how these massive AI models are learning to, watch and understand video.
Right.
And for a long time, the thinking has been that to solve the really hard problems, these models need what's called chain-of-thought reasoning.
That sort of step-by-step internal monologue.
Exactly.
Yeah.
But the sources we're looking at today show something. Well, something really counterintuitive when you apply that to video.
They really do, because video is so much about just, pure visual perception.
And here's the finding. For a lot of these big video models, just giving a direct, quick answer, it often works just as well, or sometimes even better, than that whole expensive reasoning process.
It does. And that's where the efficiency problem just hits hard. If the model is always thinking, always generating hundreds of tokens of text for every simple thing it sees.
It's just creating lag. It's wasting compute power.
A huge waste.
So the mission becomes pretty clear. We need an AI that's smart about when it decides to think. And that brings us to this new framework, VideoAuto-R1.
Which is designed for exactly that, a kind of reason when necessary approach.
And the inefficiency of the old way, the always thinking way, is really clear in the numbers. We're talking about models that usually generate, what, around 149 tokens?
Yeah, on average, VideoAuto-R1 gets that down to just 44 tokens. It's a massive improvement. But the big question is, how do you actually train a model to know when to stop thinking?
And that's the really brilliant part. It's this new training idea they call thinking once, answering twice, or TOTE.
Right, so how does it learn without a person telling it, this one's easy, this one's hard?
It sort of teaches itself.
Yep.
During the training phase, the model gives a quick initial answer first.
Okay.
Then, no matter what, it does the full reasoning step and produces a second reviewed answer.
And because both answers get scored for accuracy, the model just venture. It learns the value of that extra work. It figures out when that reasoning step actually helps.
So no manual labels needed. The real genius, though, seems to be at inference time, the early exit strategy.
Yeah. Yes. It's like the AI has its own confidence meter.
How does that work in practice?
So it sees a new video, gives that first fast answer, and then immediately checks some confidence level. If that confidence is super high, say 90% sure it's right, it just stops. That's it, answer delivered. But if the confidence is low...
That's the trigger. That uncertainty tells it, okay, time to do the deep dive.
Exactly. It kicks off the full chain of thought process and gives that more considered, reviewed answer.
And you can see this adaptive strategy playing out so clearly in the performance data.
Oh, absolutely.
On tasks that are mostly about just seeing things, visual tracking, localization, stuff in a benchmark like MVBench, the model only chooses to go into that heavy thinking mode about 25% of the time.
Right, because it doesn't need to. But then you throw something like video MMU at it,
which has complex physics, math problems.
Right, stuff from instructional videos. The think mode activation rate just jumps. It goes all the way up to 51%.
So it confirms the whole idea. Visual perception is often enough. But if that initial gut check is shaky, it calls in the heavy artillery of, language-based reasoning.
And that reasoning process can be genuinely corrective. There's this one great example in the source material with a probability problem based on something happening in a video.
And the first answer was wrong.
The first answer was likely just a low-confidence guess, but because the score was low, it kept going.
And then?
Through this really structured, step-by-step mathematical deduction, it actually revised its own answer from D to C and got it right. It forces itself to slow down and use logic.
So what does this all really mean for the field?
I mean, it means VideoAuto-R1 is getting state-of-the-art accuracy, but with this dramatic improvement in efficiency. They've kind of cracked the trade-off between being smart and being fast.
It feels like a new standard, really. Balancing performance and cost by only using that complex, expensive reasoning when it's absolutely necessary.
Exactly. When its own initial perception is telling it, I'm not so sure about this one.
So here's a final provocative thought for you to chew on. The sources mentioned that for simple visual tasks, like just finding something in a video, that whole text-based reasoning trace, it doesn't add much value.
Right. Perception is enough.
So if visual perception is often enough, maybe the next frontier isn't just about better textual reasoning. Maybe it's about finding ways for AI to do visual reasoning instantly without needing that verbose internal monologue in English. I mean, what other complex problems could be solved way faster if the AI just learned to skip talking to itself altogether?
Welcome back to the deep dive. We've just spent the last few days wading through everything at CES 2026.
So much noise.
So much. Our mission today is to, cut right through that and give you the real signals, what actually mattered on the show floor this year.
And the direction was pretty undeniable. AI was still the center of gravity for sure, but the focus shifted.
A big shift, I guess.
Yeah, a really big shift. Last year it was all agentic AI, software that just thinks and plans. This year, it was all about physical AI.
And robotics. Robots were literally everywhere.
Exactly. It's AI finally leaving the cloud and, I guess, learning how to do things.
So that's the story we're tracking today. The infrastructure battle powering this move, and then some of the, sometimes clumsy hardware that came out of it.
Let's start with the infrastructure, with the heavy hitters. NVIDIA's CEO, Jensen Huang, he unveiled the new Rubin computing architecture,
which is set to replace Blackwell later this year. And this isn't just a minor speed bump, is it?
No, not at all. It's about meeting the just the massive data demands of these new complex models.
Right.
Rubin is their play to keep dominating the AI data center.
Right.
And they made it pretty clear they want to become the, quote, android for generalist robots.
With the AlphaMeo models, right?
Yes, the AlphaMyo family. Positioning it as the open source toolkit for autonomous vehicles, for any kind of future robot, really.
It's a huge goal. But if it's open source, is it really an open ecosystem? Or is it just a smart way to make sure everyone still has to buy their hardware?
That is the multi-billion-dollar question. Meanwhile, AMD is taking a different tack.
A completely different approach.
Lisa Su's keynote was all about democratizing AI through the PC with their new Ryzen AI 400 series processors.
Yeah, bringing the processing off the cloud and right onto your laptop. They even had OpenAI's Greg Brockman on stage with them.
Which just shows how serious they are about making local AI processing the new standard.
And what's fascinating is how quickly this stuff is translating into, like, huge industrial uses. Yeah.
Oh, absolutely. Look at the Caterpillar and NVIDIA pilot program.
The Cat AI assistant for excavators, and they're training it using NVIDIA's Omniverse.
Exactly. For anyone who doesn't know, Omniverse is basically a digital twin, a full simulation where they can train these huge machines safely before they even touch real dirt.
So AI is now literally digging ditches.
Supervised by a digital copy of itself. And then you have the high-end stuff, like Hyundai's Boston Dynamics.
Right. They're working with Google's AI research lab now.
To train the Atlas robots. I mean, that's a massive convergence. You're taking the best physical robot form and pairing it with, one of the most powerful AI minds.
But if Atlas is the dream, then we have to talk about the consumer reality check.
So you're talking about LG's home robot.
I am. Celoid. It made a really sluggish first impression.
Sluggish is a kind word. People saw it placing a shirt into a dryer and then a croissant into an oven.
Very gingerly was the phrase I kept reading.
Yeah, if it takes that long to handle a croissant, we're still a long way from it being useful in a real kitchen.
Okay, so away from the high-tech hurdles, let's talk about the gear. My personal favorite was the communicator phone from Clix Technology.
The one with the physical keyboard. Pure BlackBerry nostalgia.
It just felt so good, that contoured back, the click of the keys, no more autocorrect nightmares. A real tactical choice,
I get that. And for the entrepreneurs out there, I thought the Eufymake E1 UV printer was a standout.
Okay, tell me about that.
Well, it basically takes industrial level printing on mugs, bottles, whatever, and makes it affordable for like an Etsy seller or a small business.
Yeah.
That could really change things.
Interesting. Then, of course, you had Razer with their sci-fi concepts.
Always. Project Motoko, which is supposed to be like smart glasses, but without the glasses. And Project ADA, the little AI avatar for your desk.
And we can't forget the first-timer, Lego.
Right. Lego was at CES for the first time with their Smart Play system. The bricks and minifigures interact and play sounds.
Starting with the Star Wars theme, of course.
Of course. But the big deal isn't just the toy. It's that Lego is now officially part of this high-tech conversation.
So to wrap it all up, what's the big takeaway? For me, CES 2026 is when AI officially moved out of the cloud and into real physical machines.
We have definitely left the era of purely virtual agents. And if you connect the dots, Google's AI training Boston Dynamics robots and NVIDIA trying to be this android for all robots.
You see a huge push towards standardization.
Exactly. So the provocative thought we want to leave you with is this. If every single task, from construction to doing laundry, is governed by a single open source AI operating system.
How long until that standardization actually stifles competition and true innovation in the physical world? Something to think about. Thanks for joining this deep dive. Most observability platforms are always talking about speed.
Right. How fast can you get your data? How quickly can you deploy?
Exactly. But today we're doing a deep dive into Datadog, one of the world's most critical infrastructure monitors. And for them, the real focus has shifted.
It's moved from speed to safety.
And we're going to unpack how they're using OpenAI's coding agent, Codex, to prevent those huge system-wide failures that, frankly, scare every senior engineer.
Yeah, the mission here is really to understand how AI has moved beyond just, simple mistake catching.
Like a fancy linter.
Like a very fancy linter, yeah.
Yeah.
It's to get more of a system-level guardrail. It's there to protect customer trust by stopping those catastrophic incidents before they happen.
And the stakes for Datadog are just enormous. I mean, their reliability has to be non-negotiable.
Of course. Customers rely on them precisely when their own systems are breaking.
So in the past, catching those really systemic risks, that all fell on senior engineers, right? Because the old pools, the static analyzers, they were just too noisy.
Oh, completely. They'd give these shallow suggestions that were just easy for engineers to ignore.
Right.
And that's really why they failed. They just couldn't grasp the deep context. So Datadog's AI DevX team, they brought in Codex because they needed something that could provide true system-level reasoning.
Something that could surface risks that a human just can't hold in their memory at that scale?
Okay.
Okay, so let's unpack that. What makes Codex so different?
Well, what's fascinating is how the underlying large language model just changes the game entirely. A linter looks at syntax, maybe some known bad patterns.
Uh-huh.
Codex, it sort of holds the full architectural map in its memory while it analyzes a change. It compares the intent of a pull request with the code itself,
And it's reasoning over the entire code
the
base.
entire code base and its dependencies.
Mm-hmm.
An engineer there said it was, and I'm quoting, the first one that actually seemed to consider the diff in the larger context of the program.
Wow. That is an incredibly high signal feedback. It almost sounds a little scary for an engineer who's used to working solo.
I think it's more like it's lifting a massive mental load. Engineers described a comment from Codex as feeling like, and this is another great quote, the smartest engineer I've worked with and who has infinite time to find bugs.
Infinite time to find bugs. That says it all, really.
It really does. I mean, the AI was pointing out dangerous interactions with modules that weren't even touched in the code diff.
Things a human reviewer might easily miss.
Easily miss. Or identifying missing test coverage in really tricky areas of cross-service coupling. Things that carry massive downstream risk.
Okay, so the feedback is high signal. But, I mean, you can't just take the AI's word for it. How did they actually prove that this system works against, real-world chaos?
They needed proof. So they developed this really clever process called the incident replay harness.
A time machine, basically.
It's essentially putting the AI in a time machine.
Yeah.
They would reconstruct pull requests that had historically led to real incidents, and then they'd run Codex against them.
As if it were there for the original code review.
Exactly.
So what was the outcome? What did they find? That's the bottom line.
And this is the core insight for you. Codex found more than 10 cases, which is roughly 22% of the incidents they examined.
22%.
Yep. 22% of cases where human experts had already approved the code, but later confirmed that the AI's feedback would have absolutely prevented the failure.
So it's not replacing the human. It's complementing them.
It's a new high-fidelity safety net. It's catching things that humans, looking at an isolated change, often missed. The other 78%, well, those required the kind of big architectural trade-offs that only a human can make.
Right. But proving the concept with that success rate is huge. And now over 1,000 engineers are using it regularly.
That's right. And it's fundamentally changed what code review even means at Datadog. It's not about speed or just catching errors anymore.
Which is where this gets really interesting. The focus shifts to risk and reliability.
It does. And it lets the human reviewers focus their energy on those higher-order tasks.
Architecture, design, those complex trade-offs you mentioned.
It's a fundamental change, establishing AI as a core reliability partner.
So what does this all mean for you listening? The takeaway is pretty clear. AI isn't just a linter anymore.
Not even close.
It's becoming a fundamental reliability system. It's what allows a company like Datadog to ship changes quickly, but more importantly, safely. It's about solidifying that customer trust.
It's all about increasing confidence at scale.
So here's something to mull over. If AI can consistently find these critical flaws, these edge cases that even expert humans struggle to see in isolation, what is the next critical task for the senior engineer? What's the one thing that AI can never automate? Something to think about until the next deep dive.